In this video, we are going to expand the previous code in an effort to create the full caterpillar game, step by step. We are going to keep a fixed number of food objects on the screen, no matter how long the target word is.
Hippopotamus.
This is the top-level logic used in the previous video. First, move the worm. Second, check for boundary collisions. Third, call the find food method to see if the right food is found. If it is, then get the index of the food and do something. We will group the code in the if-let block into a method called handling caught. We don't have to use the variable found. We are going to follow the same logic for our expanded code. Let's talk about some physics. There are three fields that are used for the calculation of the force driving the motion of the head. They have nothing to do with the neck and the body units. These three fields determine the strength of the force in three directions. Therefore, we are facing two tasks: calculation of the force applied to the head, and calculation of the force applied to other body parts. Let's address the second task first. Let's consider the example in which we want to calculate the force on the unit by the neck. This is Hooke's law. The force is resolved into the x and y components, which we will need later. We define a public function for the calculation of the force. The vector vec represents the segment from the unit to the neck. The orientation of the vector can be calculated like this. With the orientation available, we can calculate the deviation from the rest position and the final force acting on the unit. The calculation of this force is independent of the head, suggesting the worm is completely soft. Now I am going to show how I calculate the driving force on the head based on the keyboard press. This part of the calculation is wrapped in a method called calc input force, which returns a two-dimensional vector. This is the detail of the code. If no keys are pressed, nothing happens. The force applied to the head is 0. The variable on is the orientation of the worm, which is determined by the head position relative to the neck. This part of the code deals with the arrow up key. These two lines of code increase the value but keep the value under a certain limit. These two fields are set to 0. Finally, return the vector as the driving force. The calculation of the turning force is similar, but involves some simple trigonometry. I will skip the code handling the arrow left key. Here, I show a head on the screen coordinates. Pressing the arrow right key generates a force indicated by the blue arrow. The magnitude of the force is determined by the field right F. We need to return the x and y components of the force. Using simple trigonometry, we have the formulas for the x and y components. With the background knowledge explained, we will find the code is very simple. We slow down the worm during turning. We set these two fields to 0. We increase the magnitude under a certain limit. And finally, we return the components of the force. The arrow down key acts like a brake. Other key presses do not affect the motion of the worm. Let's examine the building blocks of the worm, lead and unit. First, let's look at the definition of the lead struct. The field's mass, Kf, and Ks are mechanical properties used to calculate the forces that drive the motion of the worm. The force itself is not a property of the lead, but rather a parameter passed to the worm. This is Newton's second law, which is used in the drive-me method. Moving on to the unit struct, which is used for constructing body parts other than the head and neck. Two methods are implemented for the unit struct. Let's focus on the pull-me method. This method calculates the pulling force and updates the velocity and position. The paint method is straightforward. Please pause the video to review the code. Let's build our worm using the lead and unit structs. This is the default trait. We will change the size and position of the neck soon. The reset method builds the worm with a head, a neck and 2 units. The head already has the default value, but we need to modify the field values for the neck. I forgot to mention the setParams method of the lead struct. This is the position of the neck. We make the neck smaller than the head, but bigger than the body units. We add 2 body units to the worm, each carrying an empty character. The drive-me method is responsible for the motion of the worm. The parameter f comes from keyboard events and is used for driving the head. Then, we calculate the force for driving the neck. Finally, we move the body units. Remember, force calculation is carried out in the pull-me method. The cross-border method checks for boundary collision of the head. Whenever the worm finds a target letter, the worm grows. First, we create a unit. The unit takes the target letter. The unit takes the position of the last element. Finally, the unit is pushed into the vector. Please pause to review the paint method. We modify the food struct by adding a field called ID, which is the index of the current food object in a vector. This vector is a field of the game struct. We change the type of the field letter back to option char. We implement the default for the food struct. This is not necessary because a struct can derive implementations of default traits for its fields using the derive attribute. Please pause to review the paint method. In the previous discussion about the update method, I mentioned the handling caught method, which manages the behaviors of the worm and the food objects after a successful catch. 3 fields are involved in this method: worm, nchars, and nchar stack. In this example, the circles here represent food objects. The word moose is chosen as the target word. Only 3 letters appear on the food objects. Nchars is the number of food objects available for the worm, namely, the number of foods which carry letters from the target word. If the worm finds a correct food object, the worm grows 1 unit, and the food takes another letter. In order to make the letters in order, a left rotation is made. Here, the second target letter is caught. The worm grows, and the food object takes a new letter. Now the char stack is empty. We rotate the letters again. After the third catch, the food receives none, and the variable nchars decreases by 1. Rotate the sequence again. This is the 4th catch and rotation. This process continues until nchars becomes 0, indicating a win. Let's examine the code. For a successful catch, do the following. Grow the worm. Assign a new letter to the food object. If the caught food object is not at the start of the sequence, swap it with the first one. Reset the position of the food object. Rotate the sequence. If no letter is received from the char stack, decrease the number of nchars. Repeat the process until nchars equals 0. The last issue to address is the bending stiffness of the worm. Before we do that, let's review how the worm moves. Currently, the head, neck, and units move in response to pulling from the preceding body part or keyboard input, with each part being dragged toward the rest point. We will add additional properties to the unit struct to simulate sideways plasticity. This is the code to move the unit. First, we calculate the force, and then we move the unit. If the worm is rigid, we expect the chain of body parts to stay straight. We introduce a field called L0 and a new method that uses this field. The parameter, target POS, represents the rest position for the current unit. The variable F represents the force calculated based on Hooke's law, which makes the unit move. So far, this code is no different from the old one. Before we proceed with the code, let's revisit the diagram we just saw. In the diagram, self represents the current unit, and the downward arrow indicates the target position, which lies on the straight line determined by U1 and U2. Now, we want to make the target position lie on the straight line determined by self and the neck. This means the worm will try to align itself into a straight line. Moving on to the code, we need to introduce a new parameter. Take note of how we define the variable, seg. Seg represents a straight line on which we define the target position for the succeeding unit. We need to return this position. Pause the video if necessary. Now that we have two methods for the unit motion, we will use both. We need to add a new field for the worm struct. Consequently, we will modify the driveMeet method accordingly. The way we control the movement of the head and the neck remains unchanged. The code in red is the same as before. Now, let's focus on the code in green. We need to take into account the position of the neck for the movement of the units. These three lines of code determine the target position for the next unit, which we call p-target. We also introduce a new variable called p-lead. Now, we are ready to iterate over the vector of units. Returning to our top-level code that manages the game activities, we make an addition. The F1 key toggles the variable, soft mode, between true and false. This is the link to my GitHub page where you can find the source code. Let's run the program.
Seal. Thanks for watching.